All right. Good evening to everyone. Magandang gabi sa inyong lahat. This is John Limhap, and I'm the community lead for the Philippine.net users group. And yeah, so welcome back to our stream. It's been a while since we've last streamed. I think the last one we've had was last September, and we had plans to stream some of our other events, but that didn't pan out. So good thing that we're back here tonight and welcoming you back. And so our speaker will is somebody who's already spoken with our group in the past, almost 2 years ago, and we will also welcome him back. But before that, yeah, I just like to share, thank some people who made this possible, this stream and all of these events. So first up is Page Up. So thank you very much for making this event possible. We'd also like to thank the .NET Foundation, who has been supporting us in this streaming. The .NET Foundation is, the umbrella foundation that helps and supports the .NET users group all around the world, and not just .NET user groups, any user group focused around Microsoft development tools. So thank you very much to them. Yeah, and we're live now in their YouTube channel. So if you want to see more, oh oops, we jumped that. If you want to see more .NET events, or and just the different catch up streams, videos from the .NET Foundation, they're involved in many different projects all around the .NET ecosystem. Please visit and join meetup.com/.NET virtual dash user dash group. And yeah, so you'd see a lot of events, especially around November. There's a lot of .NET. Usually the .NET Conf season. That's when they have a lot of events there. And yes, if you have not yet joined our social channels, please do so. Please visit our Facebook group. We also actually have a Facebook page, so you could go there. Join, follow us on Twitter. We actually have Mastodon. I've forgotten to update this, so maybe later on I can share that as well. And then of course our LinkedIn page to get more updates in real time. All right. So back to our event tonight. Our speaker is he as I said, he had joined us almost 2 years ago for the first time. And spoke about, I think he spoke about web technologies back then, but tonight he'll be talking about something, a security topic that's um not well understood by a lot of people, even myself. I would admit I'm not very well versed in this topic. So we'll be talking about cryptography 101. And so our speaker is Robert Boedigheimer. I hope I did flub that. He's a Microsoft MVP for development technologies. Um, and yeah, he's been speaking in different events and conferences. He's also I think he's a principal developer for Schwan's home delivery. So yeah, so that's what he's been doing for a long time now. So here to talk with us about cryptography, let's welcome Robert. Hi,
Hello.
Robert. I think I filled up your name. I'm sorry about that.
Yeah, it's Boedigheimer. So you were close.
Okay. All right. Right. Happy I got it. All right. I'll turn it over to you. And
Okay.
yep. So we could start the talk tonight. Cool.
All right. Let me know if you can see the screen okay. Are you able to see the screen okay? John, can you see the screen okay? Okay. Well, we'll get started here. We're talking about Cryptography 101. Again, this is Robert Boedigheimer. If you do have any questions, you can put them in the chat, and we're going to try to take them as we go. And I do have the link to the slides and the code. So I have two different variants of the code. I have for .NET Framework, and I also have for .NET, in this case, .NET 6. I need to get that upgraded, I saw this morning. And again, the important thing about that is it doesn't really matter the language, the framework. I am going to show you in ASP.NET and C#, but these concepts cross tons of frameworks, languages. They're the building blocks of cryptography. So don't focus so much on the C#. If you're not familiar with that, that's fine. The conceptual parts is what's going to matter. Again, there's my Twitter, my email, and my blog. So if you want to follow up afterwards, feel free to do so. So let's start with a little background. So cryptography is the science of keeping messages secure. And there's really 4 different main things about why would you want to use cryptography. When you talk about cryptography, most people think about confidentiality. They want to protect the data they have from being read, credit card numbers, things like that. It's also used for integrity. We want to verify that data has not been modified. It's used for authentication, and I'll show you that, identifying and validating a user. It's also for non-repudiation. So if a sender sends a message, they cannot deny later that they sent it. Again, in .NET, I'm going to be focusing on the system.security.cryptography. I talked about the .NET framework versus .NET. Very, very similar. I gave you both examples of the code. I'm going to focus on .NET. If you're using full framework, you can take a look at the code. There's not much that's different. I'll mention a few things throughout the talk. But these are all the things about why would you want to use cryptography. Next is considerations. So there's a lot of things you have to think about when you're about to use cryptography. So the first is, what's your goal? I think that's the most important because I see people using the wrong technology given their goal. So throughout the talk, I'll say, if for instance, we're going to use hashing. That's meant for validation and integrity. So if you know what your goal is, it helps you guide to what you should be using for cryptography. Think about how much your data is worth. We'll get into key sizes and stuff. I use the biggest key sizes, the most secure that I can use. We'll talk about that again. How long does it need to be secured? Is it just for the next 5 minutes, or is it something that 30 years from now, it still has to be solid? You need to think about your primary threats. So I started listing down some of the things. So again, I'm an ASP.NET developer. So these are the things I'm concerned about. In transit, obviously. So the browser over the internet talking to my servers, I want that to be secure. I don't want people to be able to access my config files. Dumping memory, modifying my web pages, reverse engineering my assemblies. That's very easy to do. If you have a .NET assembly, you can get back to what that would look like in source code. So think about those things. I mean, envision that you're the person hacking and what would they try. Like I said, I'm a web developer, so I treat my web servers like they're compromisable. On any given day, I could suddenly have a 0 day and somebody could basically own my web servers. That's my stance, so we'll see throughout the kind of things I would want to do for that. You should definitely have company security policies you need to comply with. You should also have regulatory compliance. So if you're doing HIPAA, if you're doing PCI, if you're taking credit cards, there's lots of different regulatory compliance that you need to be worried about. The next is layered defenses and how many are enough. So we'll talk about throughout the talk. I'll try to show how one thing is secure, but doing a little bit more makes it more secure. Lastly, if you take nothing else from the talk, don't write your own cryptography. So this stuff is built into languages, frameworks, it's tested. I've run into a few developers that think it would be a lot more secure if I wrote my own thing because nobody knows about my given algorithm. That doesn't turn out well. There's a lot of very accomplished cryptographers that they go write a new approach, a new algorithm. It gets vetted and they find serious flaws. So even people who do this for a living, they need to work collaboratively because it is complex to implement cryptography. So like I said, don't write your own. You'll see how in .NET it's very easy to be secure, taking advantage of what's built into .NET. So again, just please don't write your own. I'll mention this, the .NET algorithms, how they're implemented. It mattered in the past, in .NET Framework. You would have a given class and you would see these suffixes. So you'd have like AES managed, AES CNG. In .NET Framework, those meant something. So the managed meant that they wrote that particular class using C# most likely. So it's in an intermediate language. The reason that one matters is that's not FIPS compliant. So if you need to be FIPS compliant, a lot of US government work, etc. So if I were doing it in a .NET Framework and I needed to be FIPS compliant, I wouldn't want to use managed. The other one, CNG, is Crypto Next Generation. That's newer Windows platforms. It's using what's built into those. And Crypto Service Provider is for older Microsoft, like XP. Hopefully nobody's running that. But so again, it mattered back then in .NET Core and now just called .NET. All of those managed suffixes use the same operating system library. So if you're using .NET, don't worry about these at all. I'm going to show you the more generic ones you should use. If you're in .NET Framework, you may need to figure out which one you need to use based on what each of them does. Next thing is, if you're doing .NET, it is cross-platform. I wanted to give you this URL because even though it's cross-platform, not every platform implements everything. So it would be too bad if you were implementing, like I'm a Windows person. If I'm doing that on Windows, I do all my testing, I'm using .NET, I expect it to just work across platform. There may be specific classes that aren't on Linux. And so you check into that stuff ahead of time. You don't want to be surprised at the end. So now we're going to just jump into various things about cryptography. The first is hash functions. So with a hash function, it's a one-way function, which just means it's very easy to compute, but I used to say impossible in the past. I don't want to go that far. It should be hard to reverse. That's a good one-way function for a hash function. So a good example down here, I've just got a string of text. I run a hash algorithm on it, and it will look something like this. If I were to change a single letter in here, this will be a drastically different hash. And again, the idea is, given this, I should not be able to go back and figure out what that said. The hash function also is converting a variable length input, so it doesn't matter how big this input is on the left-hand side, this will always be the same fixed length, and that's only dependent on, we'll show the algorithms, we're going to basically pick how long this ends up being. So if I ran even a full book through, it's going to hash down to the same size. This creates what people call a data fingerprint or a digest, and we're going to use it for integrity and for authentication. Okay. In .NET, there's a lot of different hash algorithms that you can use. I listed ones on here that you shouldn't use anymore. So MD5 has been broken, deprecated for a very long time. SHA-1 got broken years ago, and basically the guidance, I was talking about compliance for credit cards for me, SHA-1 is no longer allowed. That's not considered secure. We're going to focus on SHA-2. So there's various algorithms. You'll see this SHA-256. This is just the number of bits of the resulting hash. So the bigger the better, and I'll show you these as we go, but we're going to focus here. Now NIST ran a contest. They basically said SHA-2 is fine, but let's get ahead of the game. If suddenly SHA-2 was broken in some way, they wanted another approach. So they basically ran a contest, I guess you'd call it. They've chosen the SHA-3 family algorithm. And so that's what you should use or you could use in the future. .NET does not have a SHA-3 implementation. Since SHA-2 is still considered secure, I don't want to go out, this is a company stance, this is a personal stance. I'm not going to go out to George's blog and find a SHA-3 implementation in .NET. I want to use what's built into the framework. I know it's been tested, so I just wanted you to know that SHA-3 is out there, not currently built into .NET. So I'm going to focus on SHA-2. Again, that's not broken at this time. It's perfectly good to use. The bottom here, it does have some keyed hash algorithms. We'll talk about what that means, but effectively it's not just your data, but also key. And I'll show you why that makes a difference. So let's jump into some code here quick. So I'm using ASP.NET, Razor Pages. I don't want to focus on any of that. You could do this in any .NET program, but I've got some simple plain text here you can see. If I come down here, that's the SHA-512. So that's the algorithm I'm going to use. If you notice, I put in the other two here, the managed and crypto service providers, as an example. Again, in .NET now, these don't get implemented any differently. So I like the very easy one here. So I'm going to use SHA-512. The way cryptography libraries work, so we all use strings, right? So I've got a plain text string up here I want to use, but cryptography libraries in .NET are using bytes. So I need to first take this string and convert it into a byte array. There's different ways to do this, and throughout the talk I'll show you a couple. UTF-8 is pretty normal, pretty popular. So I just pass the plain text. I go to UTF-8 and say get bytes. When that's done now, I have a byte array representing the original string. Then all I need to do is call compute hash. It'll give me the result here in another byte array. And then I want to display that again, right? I don't want the binary bytes. I want to show something on the screen. Again, there's many ways to do this. I'm going to show you one that I like. I'm going to use the bit converter class. So what I do is I pass in that byte array. It creates a string that looks like this. And then I'm just taking the dashes out. So I'm just going to get one long string. So if I go back here and run this, you'll see here's my string, and it hashes to this. And I just like this. We're going to use this in a URL later and some other places. So it's just a nice technique. There will be other ones that I'll show you that you can decide to use. But that's the basic hash. If I were to go in here, I could do this long plain string text. If I did that and I rebuilt again, the result would be a different hash value, but it would still be this same size because that's the size of SHA-512. Okay, and again, we like this because hashes are one way, so you can't reverse them. Where would you use something like this? So I created something I call tamper-proof query strings. And my goal is I want to protect the integrity. So we're back to the goals again. I don't care if you see what my query string is. I don't want you to be able to modify it. So an example would be, I'll just show you the page we're going to look at. You can see up here I've got, this is the query string, everything after the question mark. I'm going to focus on this. So I want to take some value. So imagine that one of those might be a customer number. It'd be unfortunate if I put that on the URL and it said customer number 12. And I use SQL Server. We've got a lot of databases that are doing sequential keys. If I showed you customer 12 up here, I would not want you to go up and be able to change it to customer 13 and see their data. So that's what we're trying to avoid here. So this is the technique we'll talk about. How do you do it? We're going to use a hashed base message authentication code. So I'm going to use hashing, but I want to use the one with a key. So the idea is I'm going to compute the hash of the query string when it's constructed. Then when I go to the page that's going to use it, I'm going to recompute the hash based on the query string. I'm going to compare the two, and if they're different, then it's been tampered with. So let me show you how that would look in code here. So to make this a little easier, this is pretty typical. You can create a library within your company of cryptography. So even though I'm using .NET, I might still want to wrap some useful functions around that. I think that's pretty typical. So I've moved that hashing code into this compute hash. So what I want is I want to have that as my query string. So I'm going to go compute a hash of that query string and bring it back so that I can put that on the URL. Okay. So if I jump into this, this is going to look very similar. I'm using a hash here. You'll see I'm using this keyed hash. And again, I'll show you why that will matter. But I'm passing in here the data. I have the choice to use a key or not. So in my case, I'm going to call it and pass a key. Otherwise, you'd just be doing what we saw before. The computer hash is the same, but I'm appending some data, which we'll get to in the future here. And then I do support different ways to send the data back. So we saw hex before. So I can do that. Again, I just created my own library for that. Another common one is base 64. And we'll see that throughout the talk. It's very familiar if you see something that looks like that. It's just another encoding scheme to take my bytes back to something I can display on the screen. So let's look at what we can do here. So the point is, by doing that, I tacked that hash value. This is the reason I liked that hex, because it sits nicely on a URL. It doesn't have any character issues. But what I want, again, is I don't want you to change this. So think about this. I don't care about confidentiality in this case. I don't care if you see these values. I just don't want you to be able to change them. So if I were to try to change it and hit enter, you'll see it blew up. Okay, a couple notes here. This is a demo. I'm trying to show you things. You would never do this in production, correct? You'd capture this error and you'd say something went wrong. If I give this kind of information out to a hacker, they're going to know what I'm doing a lot faster, because they're going to say, oh, he's using hashing, and I'll show you how the person would try to break it. But again, that's exactly what I wanted, right? I don't want you to be able to change query string values. So let's see, maybe I can come up here and just delete that whole hash, right? And again, this is thinking like an attacker. What would they do? I'm going to take that hash off and see what happens. Still doesn't work because that was not sent, right? So again, I don't want to show those errors, but thought through the threats. So let's talk about the keyed part of that. If I did not use a key, so we'll go back to the code here. If I did not use this and use a key, and again, I'll give you a warning. This is a demo. I want to be able to give you the code. I will not store keys like this right in strings in .NET, because I talked about reversing assemblies. If a hacker got a hold of my web server, got my DLL for this site, they'd be able to reverse and see strings like this. So again, I'm just doing this for a demo. We'll talk about how you can do that storage stuff later. But if I did not do the key, what could an attacker do? Well, again, if I think like a hacker, they're going to see that I'm doing right here, this hack tamper-proof. They have access to the same hash algorithms I do, right? There aren't that many. And if they were to go over here and look at the, let me pull it up here again. If they were to look at the actual value up here, they could figure out the size of this. They know I'm probably doing hashing. They'd be able to tell that this is a 512. And they would probably guess I'm using SHA-2. There aren't that many different choices. So they can come over and write their own code. They're trying to change A to 2. They could compute the hash. And if I ran this, they could then take this, go back to the original, change that to 2 like they want to, and then at the end here, they could paste in their hash, okay? That one still didn't work. Why didn't it work? Well, that's because of the key, right? We talked about layered defenses by using the, let me go into here again. By using the key and having this, I've made it harder for the attacker, right? So from a layered defenses standpoint, first of all, I'm using this to stop you from changing the query string, but you'd also have to break in my server and get this to be able to see it all. So again, layered defenses, it's just a good idea to do that kind of stuff, and thinking like a hacker helps you realize things you should do. Hash password. So long ago, I've been working on computers for a long time. When I was first looking at Unix, Unix was developed and they had a problem. They said, I have to store your password somewhere so I can authenticate you. So they said, well, we have this etc password file. Well, what they don't want is somebody to be able to go in that file, get the file, and see everybody's password. So they were saying, which should we use to do this? And they thought momentarily about encryption, which we'll talk about in a bit. Had they used that, though, they'd have to store the key for the encryption somewhere. And like I said, I don't really like that sitting on a web server. So what they said is, let's use hashing, right? This is a good idea. You type in your password. I'll compute a hash of it. I'll store that hash in the password file. Now, next time you come to log in again, you're going to type hopefully the same password. I'll hash it. I'll compare the hash for the current versus what I have stored. And if they match, you're good, right? That's the authentication. But they thought by putting the hash in there, they said it can't be reversed. So that should be safe, right? Well, what happens is people mount what they call a dictionary attack. and so they will pre-compute the hash values of the entire dictionary. So for instance, they pull an online dictionary and they say, please just compute a hash of every word in there. Let's see if what you use for a password happens to be a common word. So I'll show you what that would look like here. First, I'll pull this up. So this thing figured out that the key was secret. So let's see how it did that. So what I'm going to do is I'm going to pre-compute. So they have big lists. I mean, this is also not something that a hacker has to do all the time. There are lists out on the internet that have plain text words and what their hashes are for all of the hash algorithms, basically. Since I'm just doing a demo for you here, I was going to show how I could do it personally. So I'm just saying I think it's one of these 3 passwords. So I'm going to compute a hash, have the original, and stick them into a .NET dictionary. Then all I need to do is I have my own cracked password here. So I found this in the Etsy password file, right? That's what it's stored. And I said, I want to see if this is one of those words. All I have to do then is I call this cracked password and it says this hashed password. Do I have any matches in my dictionary? And like I said, it turned out that it was secret. And so again, they didn't reverse my hashing. The problem was the Unix developer, or the original Unix creators, didn't think through how a hacker would use this to attack them. Okay, so if I were doing this for real, I would be doing online dictionary. Thankfully today, so years ago, you could look up a user in Unix and they would sometimes put little profile data. I have social media now, right? If I were going after you and trying to attack you, I might want to just hash every word that you've ever put on Twitter or any of your social media. So there's a lot more about you that I could potentially guess you might use for a password, your dog's name, whatever. So just be aware, again, they didn't crack hashing. They were just able to pre-compute and guess what you might have. So that's kind of unfortunate, right? So the people went back and said, well, let's do something different. Let's do what's called a salted password. So they basically said, we're going to take unique random data, and we're going to also use that when we do the hash. Then they stored that salt in the password file. So for a given user admin, there's a particular salt that's different for each user. When I take your password and hash it, I'm going to use your password and your salt. I'll store that then into the password file. Okay. Well, what would that do? Well, again, it makes it harder for the attacker because they would have to figure out what my salt is. It stops primarily pre-computed dictionary attacks, right? So now that I have this salt information, you would need to now compute the hash of the dictionary and every other thing you might want to use using that salt. So it's made it really difficult for me to look at a single password file and do a comparison against all of my guesses because each person is using a different salt. So I'll show you what that would look like in code. So I have my data here that I want to pretend that's my password at this point. Here's the salt. Again, this would be different for each user. And I show you here how you can actually generate salt. So let's just jump down there for a moment because I want to mention this. If you ever try to get random things on a computer, that doesn't work out so well, right? Computers are not random things. If you try to use a random number generator in most of your languages, by default, they're pretty weak and they're not actually very random. You need to use what's called a cryptographically strong random number generator. So there's one now in .NET. There's been one for a while. Latest version of .NET changed the class. This is the one we want to use now. So I just create a random number generator. I tell it how much bytes I'm going to have for my salt, and then it just computes that salt and gives it back to me. And in this case, I said just base 64 encode it for me. So that's just a different way to show that on the screen. The rest of this should look pretty familiar. If I'm using the salt, I'm going to compute the hash like I always did, but this lets me pass that salt as another parameter to that function. So I have my data. I have, in this case, I want to get it out as base 64, and here's my salt. And again, that's different for each user. So if I were to go look at this, you can see here's a simple hash. Here's salt. I'm sorry, that's the thing we want to compute the hash of. Here would be the default hash. And again, this is base 64 encoded, and you can usually tell because it usually ends in 1 or 2 equals. You can tell that by having a different salt, this word ends up with a different hash than it would have been. Okay. I'm going to mention one other thing. I'm going to make it one step harder again. I can also just use some more random data that I store on the server. Think of it as kind of a key. It's just another piece of random stuff. So even if you had the user's ID, the user's hashed passwords and their salt, you'd also have to be able to break into my site and get access to this. So again, it's just one more layer of defense. So what has that really done? It's made it hard for me to attack the entire dictionary at once, or the entire password file, right? Now I have to go pull out, here's a hash password, here's their salt, compute all the things I want to do. Computing all of those hashes takes a while. So it made it harder for you to get everybody in the file, but it hasn't made it harder for a single user. So what I would do if I'm attacking, I go look for admin, I would take their hash password, take their salt, pre-compute everything with their salt. If I get a hit on that, the game's over, right? I'm an admin, now I can do anything I want and get into any of the other accounts. So it's helped, but it's still not perfect from protecting that. That's why this last piece is also useful, okay? So what else is done? So this is typically what's done today. It's called derived, in this case, password-based key derivation. In .NET, it's called PBKDF2, if you've heard of bcrypt, etc. It's a hash function that adds what's called a work factor. So it takes longer to compute a hash. So I'm going to show you how that would work. So I'm a Led Zeppelin fan, so let's say that's my password. You need better passwords than that, but again, this is a demo. I went and pulled some salted hex out. So now what I want to do is when I go, I'm going to take this salt and your password, I want to do a hash on it. I'm going to use this in .NET. And what this does is it takes advantage of this next thing here called iteration count. So the idea is I want to intentionally make hashing of each password slower so that when an attacker does go and say, I need to pre-compute a whole dictionary of words that you might have used, it's going to take them way too long to compute that. For me, what I need a balance. Like, how big should this number be? So I should run this on my current hardware and see, does it take a quarter of a second, a half of a second? I need to decide how long will I penalize my normal customer? Because when a customer comes to my site, types in their password, it's going to have the same delay that I'm making hackers have. So typically I'd shoot for maybe half a second or a second. So I need to run this on my current hardware and see how long does 100,000 take. If that's only a quarter of a second, I might have to make this larger then to get to half a second. So again, I'm making it intentionally slow. So this is what you typically see in modern systems that use this for authentication. They're going to have that kind of a work factor just to make it harder for the attackers to pre-compute all the values. And again, in .NET, it's the PBKDF2. You can see the class there at the bottom. So that's hashing, how we can use it, authentication, verification. I will show you one other place that you'll probably see. You've probably seen this before. So this is the capture the flag contest I was in. If you've ever been to sites that say, here's a file, and you see this is another use. So in this case, they said, I'm going to use SHA-256. I'm going to hash the contents of this file. So I know the hash looks like this. They do this so that when you download the file, you can pre-compute, or you can compute the SHA-256. If those values don't match, somebody has tampered with that. So especially on sites that do downloads, the vendor will often put out what their hash of that file is so that you can make sure that that is the right file. So this is another verification thing people will use with hashing.
Hey, Robert.
Yeah.
We do have a question from Sergi.
Okay.
Right. So if we are adding SIH. All right. The password hash, the passwords and random characters. How can we validate a password? Hmm.
Oh, good question. Okay, so when
Okay.
you're taking advantage, let me go back to here.
Mm-hmm.
So when I first take your password, so the first time you come and sign up, you're going to pass me. Let me get to the right one here. Sorry. The very first time that you come and you're creating a user account and you give me your password, at that moment, I'm going to hash it. I'm going to store the hash. I can't reverse that hash later, but when you come back, I'm going to take what you had typed and I'm going to recompute the hash for it. And then I'm going to compare the two, right? And it works whether you do salting, whether you do the extra characters, whatever. I know how to take your password and hash it into a value. When you come back, I'm not decrypting. You know, people will use that term, decrypting. That's not a hashing thing. I can't reverse the hash. So I'm just recomputing again and doing a comparison. Does that make sense? And if you're specifically talking about salt, the salt that was used would be in your password storage. So when you come back, I would take your user ID, I'd go to the password storage, I'd pull salt off. Now I have your salt. You typed in your password. I will hash it again and compare to the hashed version I have in the password file, if that makes sense.
All right. Well, we'll wait for Sergi come back to us.
Okay.
Yeah. So yeah. And just to tell everyone in the stream, if you have any more questions, please feel free to type in on the chat. All right. Hand it back to you, Robert.
Okay. Thank you. So now we're going to get into what people usually think about cryptography. So I wanted to just define some terms. Plain text is your original data. So whatever it is that you want to use encryption for, that starts as plain text. Encryption is the process that takes the plain text and obscures it into what's called ciphertext. And then decryption is the process that takes your ciphertext back to what it was as plain text. The cipher is the algorithm that you're going to use for doing the encryption and decryption. And you use this for confidentiality. So in other words, I don't want people to be able to see this data. There's a couple different classes for encryption. We're going to focus first on symmetric. So what symmetric means, and we'll look at the picture here. I have plain text. I'm going to take a secret key, run an encryption. I get ciphertext. That same key is used for decryption to get back to the original plain text. There's a lot of classes to do symmetric. DES has been broken for a long time. Triple DES is also not a good choice. I'm going to show you AES. This is what's the current US government sanctioned. It's what tons of sites use. So I'm going to show you that in .NET. It's great. The only problem is the key distributions. We'll talk about that a bit later. So let's look at how does this actually get implemented in .NET. In .NET, the symmetric algorithms are called a block cipher. So it's going to take your plain text, and the block will be a certain size. It'll take that much of the plain text and go off and encrypt it. So it's just basically doing encryption a chunk at a time. It's going to turn out that by the time you get to that last bit, it probably isn't going to magically end right at the end of your plain text happens to be the end of a block. So you have to do what's called padding. So you have to say, I don't have enough plain text left to fill the block size. So it's going to pad it with something. It can do any of these that you see zeros. I'm going to focus on this one. They just put some random data in there instead. When it comes to cryptography, random is better. And so we'll talk about that and I'll show you why that matters. In .NET, for AES in general, there's a number of different modes. One is called ECB, and all that does is it says take the first block, encrypt it, set it aside. Second block, encrypt, etc. CBC says take the first block, encrypt it, then take the output of that, some of the ciphertext, as input into the next block. So we'll talk about random stuff. Now when you get to the next block, it'll be a little more randomized. If you didn't do that, the same exact plain text for ECB that's in two different blocks would always encrypt to the same thing. So again, I'll show you an example of why this would matter. If you do CBC, you think, well, that's great. They're using the encrypted data as some random for the next block size. How do you do the first one? Well, that's what's called an initialization vector. It's just random data that's used to help that first block get encrypted. The way it works, it does not need to be a secret. So when I compute the encrypted stuff for my plain text, I'll send that in ciphertext, and I'll also send the initialization vector. It's fine that people see that. That's just the way the algorithms work. What's important, though, is never reuse an initialization vector, because otherwise, if you sent a message now with that same vector and you send it the second time, it'll end up being the same ciphertext, which is not what you want. So let's go take a look at a couple examples. So in here, again, this is symmetric. So I'm just going to show you this one first. Let's pull up the page quick. Oops, wrong one. Okay, so I'm just going to type test. I encrypt. If you notice, I took that, I got ciphertext. I wanted to show it on the screen so you can tell I base 64 encoded it. Here's the initialization vector, also base 64 encoded. I send these two things or store it, and then I can do a decrypt to get back to where I started. So let's look at what that looks like in code. So when you hit the button to do the encryption, it's going to come in here. The first thing I have to do is create a cipher. Because I'm using both encryption and decryption, I just wanted that to be in its own reusable function. So I'm going to use AES create, and it shows you what the defaults for that are. I'm going to change the padding to be the more secure and random. And then I'm going to take a key again. So again, we're not going to actually store this as a string. This is our secret key. So I'm taking that, it's hex encoded. I'm just getting that back to be the bytes for the key. Once I have the cipher, the actual work to do the encryption is pretty straightforward. If I look here, I create an encryptor first. I do what we always have to do right here. I have to convert the string into a byte array. We saw that before. And then I do here the actual encryption. So now that I'm done doing those steps, it is encrypted. And it's in this ciphertext. And then I just chose to base 64 the ciphertext so I could show it on the screen. So what I want you to see here is this is not a lot of code in .NET to use a well-known, securely, it's been tested. I can take advantage of this and not have to write my own things. Okay, and again, if I were in a company, I would create a library that had just, here's encryption, give me the key, which would make it even simpler than what you see. Okay, so we'll talk about the bad modes again. If I were to come in here and change these lines, if I said padding of 0 and do ECB, every time I do an encryption, it will end up being the same. So if I go up here right now and say encrypt, you'll notice every single time, because I'm using the CBC mode, it has a different initialization vector, so I end up with different ciphertext. Otherwise, if I sent the same, like say there's only 5 messages I want to send to somebody, after a while they'll know this is the ciphertext for those 5 things. They're all the same. I want to make it so that even the same values being encrypted are different by using that mode. So we talked about ECB. This is kind of the famous why you shouldn't use ECB. So we got the penguin on the left-hand side here, and you can go check out all the what's evil about ECB out here in Wikipedia. ECB is taking a block and doing the encryption. Because they're not randomizing it, every byte here is going to get changed to a different byte, right? But every white here is going to be the same value. So even though this is encrypted with ECB, you can still make out that that's a penguin, right? Because each one of the same values, it has a different value, but it's going to turn out being the same. So this is why you don't want to do things like that. You can see things when it's done in ECB mode because it repeats the same encryption for every block. And you can see if you do CBC and others, it's completely randomized. Okay. So that is symmetric algorithms. So the problem with the symmetric was, how do I distribute that secret key? So let's say I looked in the chat, one of you asked me a question, and I said, I'll send you this secret message. how would I send it to you, right? Somehow I have to securely get you a key, which isn't easy to do in a lot of situations. So instead, they created what's called asymmetric algorithms. So let's look at the picture first. I'm going to, each person is going to create a key pair, one of which is public and one of which is private. So I would send to you in chat and say, please give me your public key. I would take my plain text, your public key, I would encrypt it. We have ciphertext. And it's asymmetric now, so it's not using the same key to decrypt. In this case, it's going to use the receiver's private key. So they should never give this out. They put this wherever they want, email signatures, LinkedIn, etc. The only person who can decrypt this is the person who has this private key. These are related to each other. You can't derive one from the other easily because of how they do the derivation stuff. But I would keep my private key secret. I can do the decrypt and get back to the original plain text. So this is great. It solves the key distribution problem. There's a couple problems with it though. It's about 1,000 times slower than Symmetric. And there's also limitations on the data size. So there's limitations based on algorithms about how big the plain text can be. But so this is kind of sad, right? That it's easier to do your key distribution. Unfortunately, it's a lot slower. I'm going to show you a couple different algorithms in here. I'm going to focus on RSA as a pretty common one, so I'll show you that. So let's go look at this code. So when I come in and do the encrypt, again, I'm just going to do a one line or a function called create cipher. And if I go up here, it's very simple. I just do an RSA create. I need to give it a key. So in this case, this is the person's public key. You can represent RSA keys as strings, look like XML strings. So what I'm going to do is, this is who I'm sending to. It's the receiver's public key. I just put it in a constant here again for demos. The encryption is pretty straightforward then. I have to change from string to a byte array. I do the encryption. Just to note, use this padding. I put out here a note, the other kind of default padding is no longer considered secure, so use this. And then I base 64 the results to show it on the screen. And again, here's the decrypt. So again, if you look at this, that is not a lot of code to use RSA and the public key asymmetric to be able to send each other messages. Again, that's why you don't try to write your own stuff. It's straightforward. The stuff's been tested. So that's asymmetric. When would you use this? So one practical example is if you gave me a credit card number, I have to take it on my web server. I want to encrypt that because we're talking about confidentiality. I don't want you to be able to see my credit card number. I can generate an RSA key pair. I'm going to keep the private key inside my network on a very secured system so it never gets exposed. I can put that public key out on my web server. So I like this because it's a public key. If they took over my web server, they wouldn't get access to anything that could do the decryption. Had I used Symmetric for this, so we talked about the password storage and other things. If I would have used Symmetric encryption for this, I would have to have a place on my web server where I could store that secret key. Not a great idea, right? I told you those web servers I think are compromisable. So this is just one thing you could do. Create that key pair, store the public on there. So let's look what that would look like for code. So again, this is a public key. That's what I'd put on my web server. And we saw the same stuff before. I'm going to create the cipher like we did and do the same encryption. So if I show you what it looks like here, I'm going to run this. Whoops. Just clicking the wrong one here all day. So if I want to use, that's the basic asymmetric. Here's what I do. I take your credit card. super secret credit card number. So this is the web server. It has the public key. As soon as it does the encryption, the only person who can decrypt it is the one who has that private key. So imagine you're doing this, you're storing this stuff in a database somewhere internally behind firewalls and such. You're going to have a decrypt right before you'd send it, say, to a credit card processor, and you're back to where you started. So this is a practical place you can actually take advantage of using a public key and reduce some of your risk. I forgot to show you this before when we were talking about random number generators. Since computers are not good at random, Cloudflare, if you're familiar with them, actually has this lava lamp wall out in California. When they need to create random things, or when they need random data to help them make random things, they'll take a picture of this and digitize that, because the current state of those lava lamps adds randomness that a computer wouldn't have. And then I saw another one where they actually use pendulums. So this is another instance for them. They take pictures of these pendulums to get some random data again. So just cool practical places about generating random data and how people do that. Next I want to talk about is digital signatures. So here I want integrity and non-repudiation, which just means I want to prove, let's say I'm sending you a contract. I want to prove to you when you get it that it hasn't been tampered with, that's the integrity, and you want a digital signature proving it came from me and not someone else. So that's what digital signatures will give you. You basically are going to, if we look at the picture down here, I take my plain text, I'm going to use your public key like we did before. So I'll mention this. I'm also using confidentiality for this. That's not part of digital signatures. You don't have to do it, but typically when you're sending something that you care about, you want confidentiality as well. So here's the high level that does it all. I'm going to take your public key. I'm going to encrypt your plain text, get a ciphertext. That's just what we saw with asymmetric. It uses hashing now. So it takes your ciphertext, computes a hash. That's my hash value. The way the digital signature works, key pairs are just opposites of each other. So in order to get the encrypted for the digital signature, I'm going to use my private key to do that encryption, and that's the signature. So that way when you get it later, you can prove that I'm the one who signed it, because the public key you have for me lets you decrypt what I did with my private key. So once this is all done, I would take the ciphertext and the signature and send it along. So let's look at what that looks like in code. So here's my sender. This will look pretty familiar. Receiver's public key. Normally, again, this would be in a database or somewhere. I'm just giving it to you as a demo. Here's the sender's key. This is my private key. So again, I wouldn't normally store it in a string, but I've got it there. So the first thing I have to do, I create an RSA cipher like I did before, and I give it the sender keys. This is what I'm going to use when I send to do signatures. This is what you saw before. I'm going to take your public key of who I'm sending it to, right? So now I have these two different ciphers set up, one using your public, one using my private. Here's my super secret message. I'm going to convert that like we always do from a string to a byte array. I'm going to do encryption. So I'm going to use the normal RSA. I'm going to use the receiver cipher, which is your public key. So when I do this now, I have confidentiality, right? I'm just being nice and doing that. That's not necessarily something you have to do with a digital signature. So now I have this encrypted. Now I'm going to use some hashing. So I do the SHA-512 like before. I'm going to compute a hash of the ciphertext bytes. So the encrypted stuff you hash, and then I'm going to sign it. So I'm creating in .NET, I'm using this class, telling it to use SHA-512. That creates your signature. And then here's the ciphertext and the signature as base 64. So again, this is a lot of stuff going on here with not a whole lot of code, right? and I get all of these benefits. I've just sent you a contract or whatever that people can't read. You can prove that it's exactly what it said when I sent it. It hasn't been tampered with. And now we can also prove that I'm the only one who could have signed it because I'm the only one that has my private key. So that's cool. Let's talk about practical uses of cryptography. A good example is HTTPS. So the way our browsers and servers communicate to make sure things are secure. If you're the provider of a website, you'll get a certificate. So you go out to Let's Encrypt, wherever you want to get a certificate for your server. And all that a certificate really is, it's the public key for my web server. So I generate the same like I did before, public-private key. I take my public, I go to Let's Encrypt, they digitally sign using their key. So that basically they're attesting to, they know that this is Robert's site. Here's the public key for that site. They sign it, so they can make sure it hasn't been tampered with, and I can prove that it came from Let's Encrypt. The browsers have what's a well-known list of certificate authorities. So it says, I trust Let's Encrypt, whoever else we want to trust with certificates. Browsers know those certificates, so they can use the public key to prove that that was signed by the certificate authority and that it's definitely ours. So what really happens, that certificate sitting on my web server, the browser, it's going to go through the TLS handshake. So this is actually the protocol that does the encryption, TLS. The browser is going to first go out and get the server's certificate. They're going to validate that it was signed by a reputable certificate authority. It's going to pull out the server's public key. Then if you remember back to what we talked about, I don't want to use asymmetric for our whole discussion because it's too slow. So the trick is the browser creates a new symmetric key, encrypts it with the server's public key, and sends that to the server. The server can decrypt it and get out the symmetric key. So now we both have a secret key. We just used asymmetric and all of these other things to be able to get that newly created symmetric key from that browser to the server. Now those two talk to each other using symmetric, which is much faster, but we've avoided the key exchange issue in this case. So it's just a good example of all the stuff we've talked about so far is incorporated in what people use for HTTPS. By the way, I'll say one more thing. If I back up, I forgot to mention this. This is a one-on-one talk, so I didn't want to get into it too much, but the way people do hashing today, it's authenticated hashing is a better choice. So I can find where I have my, if I can find it, now I gotta find it. Oops, wrong place. It combines hashing with AES encryption. So you get the advantage of it. You can tell it hasn't been tampered with. So I'm going to just tell you that this code is in here. If you want to take advantage of being able to do symmetric that's more advanced, just check this out. It has what I would say is a much newer approach. I just wanted to start with the simple way first. Talk about keys and key sizes. So from a sizes perspective, you get to choose. So if I choose AES, I could use 128 bits or I could use 256. I'm not going to get fired over it being a couple milliseconds slower, so I go for the better security. So if you take AES 128, if you're not sure, take it and run it, right? Taking it AES 128-bit versus 256. The 256 will be just very small amount slower, but each bit that you add makes it exponentially harder. So the 256 is not just twice as good as the 128, it's a ton better than 128. Same, so I just go with the highest that are available at this point. RSA, I use 4096. So now we talk about key storage. So I'll just admit key storage is by far the worst thing in cryptography because there just aren't a lot of great answers. If you're using Azure, you can use some of their key stuff. Kind of depends on where you're deployed. In the web form days, there was the ability to take an app settings section in your web config. You could encrypt that. So it gave you on-disk protection of some of the stuff that you'd put in this field. So key storage, like I said, if you're on a certain system, they might provide a way for you to do that. Otherwise, it's very difficult. That's why when I talked about a website in public needs to encrypt a credit card, I avoid the whole secret key issue by using the public key on the web server. So it's more of an avoidance technique because I don't trust that someone couldn't take over my entire web server. So I won't say a lot more about that. Again, lots of things to be considered when you try to decide where to store your keys. So in summary, if you take nothing else from the talk, please don't write your own cryptography. Like I said, a lot of very trusted cryptographers have made mistakes. So just please don't do that. Use trusted algorithms and implementations. Like I said, .NET does not have a SHA-3 implementation. I'm just not going to go find somebody who randomly says they implemented it okay. I'm going to use what's in .NET. Someday .NET will support that, and then I'll consider when I want to move. Think about what you're trying to do. So if you're trying to do integrity or do authentication, you're using hashing. If you need to use encryption, generally you want to use Symmetric just because it's so much faster and you can do a lot more data, but you can use Asymmetric when you need to do things like digital signatures, key exchange, etc. And then the last thing is know your threats and choose proper countermeasures. So about, I think it's been 2 years now, I started doing capture the flag competitions just because the whole point of those is to safely, in some environment, practice out your hacking skills. It's really given me a different perspective when I think than as an attacker looking at what I do for security. It's made it a lot more interesting now that I understand how people are actually attacking and I've actually done it myself. I can go back to my site and look, here are my threats. Am I doing the proper things? Do I need more layers? Those kinds of things. I do have a Pluralsight course, Intro to Cryptography. I listed some good books here. So I like this one. I actually don't know Python, but this book is recent and it gives a lot of details on practical ways to use AES and all the things that we talked about. So it's just a good book that tells you in real life doing this stuff, what works and what doesn't work. One of the best original books was Applied Cryptography, Bruce Schneier. It's older now. Still has good information on things like how to safely use AES because AES has been around for a long time. I don't care about how it all works. I don't care about the math and all the complicated stuff. I just want to use cryptography correctly. If you care about all the math and exactly how the block ciphers and all this stuff are implemented, this is a good book. These three essentially all go into the details of how does AES actually work and such. And like I said, I don't care. I just need to know how to use it properly. These are some good books if you're into reading about cryptography throughout history and how things were broke, like how was Enigma broken for World War II. Some very good books that I find it interesting to look through and see how someone tried to do things securely and then how that was broken into, just that progression. That kind of stuff is covered in those books. Again, there's my Twitter, there's my email blog. Here's the link to the slides and the code. And again, there's .NET 4.8 framework, and there's also just plain .NET. Okay, so if you have any questions, we can go through those now.
Right. Thank you so much, Robert. Yeah. Actually,
Welcome.
there are questions.
Okay.
Following up to the original question by Sergi, I think
Yep.
he asked. Yeah, he was clarifying, but if it's regarding those random salts, so we talked about earlier.
Yep.
If they're random, that means that means that it's different per user, right? And then to
Yes.
follow up on that, Bangon Kali asked if is it typically safe to store the hash password and the random salt, because that's how they imagine that you would be able to retrieve the random salt that you had added to specific password. So what's the best practice, I suppose, for that?
Yeah. So I guess let me answer the first one. The demo I gave you here, when you create an account, I would do this generate salt just the first time when you make your account. And I'm going to store that then along with your hashed password wherever, right? Database, the password file, whatever. So I just use random the first time you came so that I got your salt. Now that I store that, I store both of them. I'm going to have the hash password and the salt sitting somewhere. So when you come back, I'm going to find your user ID, pull out your salt. So every time you come, I'm not making random for you. I'm just making random for each user's. The first time they make their account, I'm going to generate it randomly. That becomes their permanent salt that I'm going to then store in the database. So hopefully that helps with the first question.
All right. All right.
The second question is it a great idea to store the salt? I'm just going to talk about Unix first, but when they did the password file, that's where they stored it. They made that file readable to everyone. So again, just from a layered defense, why would you do that, right? Why is that smart to let people look at all the hash passwords and salts and stuff? So typically now I can't see that, or I'd argue hopefully you don't make that accessible. From an algorithm standpoint, it doesn't, I gotta say how to word this. You have to have the salt stored, because when the person comes back, I have to know which salt I use to first hash your stuff. So I have to put the salt somewhere. The best practice stuff, I would also do something like this where I stored something else on the server. So that's another safety check, right? But you could go in, take the hash password, take the salt, and pre-compute everything. Again, the salt only makes it harder for me to go after every password in the file at once. It doesn't really help me with you. Like you said, once I have your salt, you still better have a good password, right? If you don't, I'll be able to do the hashing. And so I don't know if that helps the second question or both questions, if people want to follow up
Yeah,
on what I just said
I
there.
suppose. Yeah, I suppose it's just they were clarifying whether it really means that that it's random, right? Um,
Yeah,
I
so
do have.
it truly
Yeah.
is random salt.
Mm-hmm,
When I created your account, I got you using this class.
mm-hmm,
I got you a serious randomly generated salt, but I'm storing that in the password. This is just, again, I had to do this for a demo. Imagine this salt really, it's your salt is coming from the password file or the database. It's
mm-hmm.
not random to you every single time. It's just random
Yep.
the first time
Yep.
you make an account. So
Yep.
hopefully that helps.
Yep. Awesome. Yeah, Sergio says it's more. It is more clear now. So,
Okay. Thank you.
all right.
Thank you for following me
Great.
up. And by the
Great.
way, if you do, as you look at code, or if you think of something you want to talk to me, you can hit me up on Twitter or emails or whatever as well.
Yep. So I'm gonna flash that again. I do have a few questions of my
Okay.
own
Sure.
about this. So one of the things that I had been reading about is that there are claims of, some especially specific governments. I won't say who,
Yeah.
but about advances in quantum computing and how effective those quantum computers would be, or how practical they are for breaking all of this. I mean, all of the cryptography and encryption technologies that we have now are reliant on how long it takes for these algorithms um, to be reverse engineered or broken using traditional binary computers. But
Right.
with the advent of quantum computing, supposedly the exponential times of needed to break those algorithms will go down. Yeah, it's
Yeah.
just a hypothetical of how far in the future do you think that threat would be? Or,
So it's a common question that people have, and I pulled up the slide of the one that cryptographers are most feared is really around asymmetric. So we didn't talk a lot about these key generations.
mm-hmm,
Typically, they're large prime numbers,
mm-hmm,
and those are on current computers trying to guess given a public, trying to figure out the private, all of that stuff it just takes way too long on a current computer. They're afraid in the quantum world it'll be easier to factor primes and such, and be able to figure out the private key for a public key. This is just really not a current hardware. It's not a risk. They're speculating that on quantum, this would be the first area that would have some problems. As far as when, I mean, quantum, we don't have access, or I don't, to quantum computers today. I haven't heard anybody say that now that I have quantum, I was easily able to do this, right? I have not heard of an actual with somebody with a quantum. But that's the risk, is that they're going to be able to figure this out faster in a practical amount of time compared to what they could today. So I was kind of in fear of that, but then somebody pointed out that when you have quantum, you're going to have better options to create more secure cryptography, right? Theoretically, you could do things you couldn't do today that would also improve. Like, as things have gotten faster in the past, it made it better for how you encrypt as well as how people decrypt. So they're kind of holding out hope at some point that will save them. I would say everything you had encrypted up to that point with your RSA keys like that is what they're worried about with quantum.
Yeah.
But yeah, I don't have a good answer. Like, when will I have a quantum sitting on my desk and be able to figure this out for most sites? I don't have a good answer for that. But the stuff I've looked at, that's usually the first thing people say is, I hear this is all going to break with quantum. And I think that's a little nuanced, some of them. And again, they usually point to this one as the one they're most
Yeah.
concerned about.
They're most
But
concerned about.
right.
Yeah.
I would
Definitely.
think it would impact, if we go back to this too, if they're just straight out faster than they used to be, you'd also have some, I don't hear about this from people, but again, this work factor hash functions, those will be, in theory, those may be faster too, right? And I'll just have to change if I go back into over
So
here.
so change the algorithm to something like PKBDF and
Yeah, and
every.
when we're talking
Yeah.
about
Right.
salting and all that kind of stuff, I mean, the real world people are using algorithms like this with salt and whatever else, but this is the magic. So I also won't mention it, but a password manager recently has been in the news about having their stuff stolen.
Yeah.
And one of their recommendations was they used to use 100,000 iterations. They recommend now you go in their interface and ask for 600,000. So they're looking kind of at
Okay.
current hardware. It's a one-on-one talk, but I will mention, if I did this, I stored your hash, it used 100,000. Now next week I say, gee, I better change that to 500,000. There's a transition period for that, because
Yeah.
if I
Definitely.
just change that to 500,000, my current stuff, I wouldn't be able to compare hashes anymore. You have to think through how you're going to go from one iteration count to another,
Yep.
if
Yep.
that makes sense.
Definitely. And you definitely have to think about the impact to that of that too. The
Right.
apps that you have there for retrieving the information, right? Those would go slower as well. So yeah.
Yep.
Okay, that could definitely happen. All right. Next question. The that I was really and that I'm really curious about. And this goes back to the HMAC HMAC 512 stuff.
Yep.
Um because a few years ago I had this project where we were uh um building up a public API, and one of the ideas that came out of that is to use the for example, if you have a post request, right, and there's sensitive information in that post request, um one of the ways to probably secure that is do an HMAC of the body itself and then bring that along with the request as some sort of header to verify if the body had in any way been tampered with or so. And but ultimately the path that was taken was Make it simpler. Just use the usual bearer token way of method of securing the API call, and just rely on um, I think at that point was TLS 1.2 was just coming out. So just rely on HTTPS and TLS 1.2, right? Where does that practicality, where do you draw the line of how hard is this to implement
Right.
this, how secure it is?
Yeah, so we go back to the layered defenses and how many things should you have in place. So you certainly want to have HTTPS in that
Mm-hmm.
conversation so that
Mm-hmm.
your actual traffic is being encrypted. Um, there are people that do, so I didn't mention it, with HTTPS you can do client auth as well. So not only are you proving it, the server is who,
Yeah.
it's the domain you think you're talking to, you can also issue digital certificates to the client. So they
Mm-hmm.
have to supply those certificates when they first send requests. So it'd be kind of another level of authentication that you are someone
Mm.
that you're supposed to be, because you own that certificate, right?
Okay.
That you're also
Yeah.
going to send during the TLS handshake. So people do that. If you're talking about doing encryption from the client, well, I'll answer your other one. The HMAC would be if you wanted integrity, right? So if
Mm-hmm.
you said, I'm going to use HTTPS, but I'm concerned that as an additional level, I want to let you make sure it hasn't been tampered with, right? In that
Mm-hmm.
case, you could get that by doing the HMAC on the client, but you have to have the secret key down on a client now, right?
Mm-hmm.
Which is kind of problematic. I'm just going to see the other thing that you were talking about. So TLS and a lot of those, and again, I'll flip back over to, I want to find my, I want to see, I'm looking for something in particular here. Not the HMAX. I'm not finding what I want to find here. But yeah, those are some of the
Mm-hmm.
trade-offs, right? Of
Yeah.
how much is it worth putting digital certificates on the client when you have HTTPS. There are other things where client do things called certificate pinning. So inside the client, it knows that it's talking to a certain certificate on the server. That's an option as well. The
Mm-hmm.
TLS stuff has, I'm trying to remember the TLS stuff that helps you. Okay, so this will be HTTPS uses TLS. I talked about the uh, AESGM, which is in Symmetric, where I mentioned that there's this other algorithm people use. If
Mm-hmm.
TLS is using AES-GCM, that gets some integrity built in by default. So this is
Okay.
also, and people are using this. And if you look, I got to think of I'll just look and see if I can find the site. I'll just pick on Bing. Not responsible for whatever content might be here. It's going to hit F12. If I go into the security right here. So
Mm-hmm.
Bing is actually doing TLS 1.2. They're using AES 256 GCM. This is the
Mm-hmm.
encryption that has hashing built in.
Oh, all right. All right.
So if you
Okay.
carry this back to, because you kind of said two things, and you want to make sure it hasn't been tampered with. I wouldn't use an HMAC to do that, because if you support AES GCM, the integrity stuff will already be incorporated. So you'll know that it wasn't tampered with. If you wanted to do, I've had people ask me, should I double encrypt, right? Should I encrypt on the client
Yep.
and use
Yep.
HTTPS? It's back to you. It depends on how worried you are. I personally am putting my stake in the ground that I'm going to trust TLS, and I wouldn't personally do that. I wouldn't encrypt it on the client and use this, solely because the client side storing that secret key would be very problematic, right? Somebody
Yep.
could get at that pretty easily. That I don't know that the effort there is worth it for me for what you would gain compared to just relying on the TLS and these types of algorithms, if that makes sense.
Yep. Yep. Great advice. Thank you.
Mm-hmm.
All right. And yeah, there is actually one last question
Okay.
here that I will answer. Is salt and pepper still relevant today? I will say please add MSG to it. Uncle Roger fashion. All right.
Yes.
All right. I guess that's all the time that we have tonight for the questions. So thank you so much, Robert,
You're
for
welcome.
that great talk, and thank you so much for accommodating us. I think it's what 5 a.m. your time.
Yeah, it's 6:21 now. Yeah.
Okay, okay. It's already 6, but yeah, when we started, it was
Yeah.
5 on your end. So yeah,
A little
we'll
early,
let
but
you go
that's
back
okay.
to. we'll let you get back to bed now.
All right. Well, now I have to go to work. So,
Yes, of course. All right. So thank you very much, Robert.
yeah, you're welcome. Thanks for having me.
All right, sure. All right. So, thank you very much to everyone that had stayed on. And yes, I hope you learned a lot from that from that session from Robert. It's really good. There's a great mix of things old and new that we learned tonight. But definitely that advice that Robert gave about do not write your own encryption that has been around for forever, and please take that advice. Use something that everyone has already tested in the field, right? So with that, we will end tonight's session. So thank you very much to everyone who had watched this, and please go back to our social channels and to our meetup.com. Watch out for our next events. Right, with that, I'll say good night now. Thank you very much. Magandang gabi sa inyo lahat. This is John Limhap from the Philippine.net Users Group. Bye bye.